welcome and thank you so much for being here. Um, so this is the kickoff of the second lecture series as part of the top webinar, and the topic this time is on the level set method or level set methods for topology optimization, and the recording is currently live on YouTube and it will be available there later as well. And as always, you can follow along on our newest plans on the website and register for the mailing list there as well. And I'm currently trying to move to a more automized mailing list system. Today we have the esteemed Professor Grégoire Allaire and also senior researcher Charles Dapogny. So I think Grégoire needs no introduction, and if I were to do it justice, just like Ole, we would be here all day. So I'll give a short one. So Grégoire has been one of the influential mathematical voices in topology optimization for several decades. And his work began in the late 80s with homogenization theory, and he was also among the sort of pioneers who brought topology optimization into the mathematical sort of mainstream, you could say. And he's perhaps best known for his contributions to the level set method for structural optimization, and he has also continued working on bridging homogenization and optimal design. And Charles was a PhD student of Grégoire and has been contributing to bringing level sets into the newest generation with remeshing, which will be the topic of the third lecture. Um, so the lecture will be around 45, 50 minutes long, so 50 minutes long, and then we will have questions afterwards. Please use the Q&A button. So at the bottom of your screen, you should see a Q&A, like a question mark. You can press on that and enter your question during the presentation, and then we will take it at the end. And if we have a lot of questions, we may go a little bit over time, but I will try to keep the time. Okay, and with that, Grégoire, please, if I stop sharing, then you should be able to take over.
Excellent. So thank you very much, Joey, for the introduction and for the invitation. It's a great pleasure to present this series of 3 lectures on the level set method for structural topology. And it's a pleasure to do it with my former student, colleague and friend, Charles. All right, so I don't think I need to say a lot about shape and topology optimization and its importance in the design of a physical system. You can see here a picture which has been done by some of our colleagues at ANSYS, and level set method is one of the method. Of course, it's a bit later. It appears a bit later after the density function method like homogenization or SIMP. But it has some advantages. And to introduce a topic, let's say that it is based on 2 ingredients. A first ingredient, which is the Hadamard method for geometric shape variation, that I will very briefly discuss today, but which will be mostly the topic of the next webinar. And then the second ingredient is the Osher-Sityan algorithm for advecting level set functions, which was existing some years before it was introduced in the context of shape and topology optimization. Okay, maybe just a teaser, this movie on a classical cantilever problem, where you can see the evolution of this kind of Swiss cheese initialization that moves. So topology change, as you can see, you have also some slight oscillation that I will explain maybe later or in the next lecture. Good. So the content of the webinar today is to introduce the level set algorithm for interface capturing, then explain how it can be implemented in the context of shape and topology optimization, and then show some numerical experiment. The next second webinar will be about how you compute shape derivative by the so-called Hadamard method, and then all the advanced tricks when you implement a level set algorithm, the question of extending the velocities, the choice of the optimization algorithm, the fact that you can use more general mesh, simplicial meshes. All those very important details will be discussed in the next webinar. And then the final webinar, the third one, will be about the last variant of the level set method, which is based on remeshing, and then meaning that you always do computation on a body-fitted domain. So the mesh is always perfectly adapted to the level set and so to the geometry of your shape. Good. Level set method were introduced around the end of the 80s, so probably in 88, something like this, by both Osher and Sitian for interface capturing. And you can see on the top some pictures of bubbles that, after 3 instants change shapes. And so it was really used first for a combustion model and fluid mechanics model. But of course, it has been introduced a little bit later, early 2000, in shape and topology optimization. And today we are going to discuss some first presentation and first numerical experiment about this. Let me start with a basic principle, and let me first present the setting of shape and topology optimization. So a shape for me is a domain omega in R2 or R3, and a shape and topology optimization problem is a minimization of some objective function, some cost function j of omega among various shapes omega with constraint. And for simplicity, let me only consider equality constraint. Of course, inequality constraint are completely similar, also sometimes a bit harder to treat from a numerical point of view. But today, I will not discuss that much constraint. That will be the topic of the second webinar. And I will discuss mostly unconstrained problem where I minimize an objective function. There will always be a volume constraint, but further constraint will be discussed next week. Of course, the difficulty of the business is that usually the objective function as well as the constraint do not depend directly on the shape, but they depend on the shape through a state. For example, the solution of the elasticity equation in your domain omega. And so that's a very indirect, implicit, nonlinear, and non-convex dependence that makes things a bit hard. Okay, so here is the first example. That's the first example of thermal conduction. And so instead of being a shape optimization problem, it's really an interface optimization problem. You can see here a square domain, which is filled by 2 different materials, 2 phases. Typically on part of the external boundary, you have a Dirichlet boundary condition, so the temperature is fixed to be 0. The remaining part of the boundary is isolated, so it's a Neumann boundary condition, a homogeneous Neumann boundary condition. And then you have, let's say, a source term f inside your domain. And then you want to find the best arrangement of the 2 phase alpha and beta. So, for example, you minimize the average temperature. So if you minimize the average temperature, in some sense, if the phase beta is a good conductor compared to the phase alpha, which is a bad conductor, so the phase beta is yellow while the bad conductor alpha is red, you want to have a kind of a geometry of the good conductor that will extract heat, which is produced everywhere, up to the Dirichlet boundary where heat can be evacuated because you have the fixed temperature equal to 0. Okay, so in this type of problem, it's not the external shape of the square that you want to optimize, but it's the interface between the two phases. Now, a more classical example in solid mechanics is where you indeed have only one phase, and outside this phase, this is void. And so you are really doing shape optimization. So for example, you have some part of your structure here, gamma D, which is clamped. And on some other part, gamma N, you have some applied loads. And then all the other part are free boundaries, so Neumann boundary condition. And what you want to do, if you solve the linearized elasticity equation in your domain omega, the solution u omega is a displacement, E of u, which is a symmetrized gradient, is a strain tensor. For simplicity, I assume no bulk forces, and I simply have a surface load on the boundary gamma n. And a classical objective function is a compliance, which is either the stored elastic energy or the work done by the load. And you want to minimize this with a volume constraint. And on top, you have a sketch of a classical 2D cantilever, but below you see a more complicated pylon that we will discuss a bit later in this talk. Good, but there are many other possible applications. You could also do shape and topology optimization in fluid mechanics. On the left, you have an example of a heat exchanger. So the white parts are a kind of an obstacle where you can extract heat, which is carried by a fluid outside those white obstacles. On the left, on the right, sorry, you have an obstacle inside a fluid flow. And of course, nowadays, other applications, like let's say for electrical machine on the bottom left, or for a nanophotonic converter on the bottom right. So there are many other possible applications of structural optimization using level sets. Okay, so one of the ingredients of the level set method is a method of differentiation with respect to the shape, and let me explain the basis of this. Of course, you know that when you optimize a function, you need to compute a derivative. So here you have a sketch of how you compute the derivative f prime of x of a function f defined in R2 with value in R. And so you do a Taylor expansion. So by computing f of x plus h, and you do a Taylor expansion like this. So that's very classical. But of course, when the optimization variable is a shape, what is a small variation of a shape? You cannot do addition of shapes. There is nothing like a vector structure on shapes. So what is a convenient way of defining increment and computing a derivative for a shape functional? This was provided by Hadamard at the beginning of the 20th century. And the idea of Hadamard was to look at a variation of a shape with respect to a reference shape. So on this picture here, you see a reference shape with this black boundary, omega. And then you look at very specific variation of this shape omega, which are called omega index theta, and which are defined as identity plus theta applied to omega. What does that mean? That means that any point x in omega is displaced to a new position, which is x plus theta of x. So theta is, in some sense, an increment, a displacement for the shape omega. And so you obtain the new shape with a boundary, which is a red dotted line. And every point x, which was on the boundary of the initial domain omega, moves to a new position x plus theta of x that defines the boundary of the new shape omega theta. Okay? So in some sense, we are looking at a very specific class of variation, which is kind of a restricted class of variation. And those variations are parameterized by this vector field theta, which we assume to be smooth, let's say C1, in the sequel from RD into RD. And then, oops, sorry, excuse me, I'm going too fast. And then if theta is small, a very classical result is that omega and omega theta have the same topology. It's well known, that's one definition of topology, that if you make a continuous deformation of a given domain, then this continuous transformation has the same topology. So topology in 2D means the same number of holes. In 3D, it's a bit more complicated. It means the same number of holes, handles. Okay, so I will not go too much into details here, but there is this very well-known book by Henro and Pierre about shape variation and optimization that you can look at if you want more details on those aspects. Good. And then the definition of what is a derivative is it's going to be a derivative with respect to this variation, to this parametrization of the variation. So a derivative with respect to this vector field theta. So the definition of a derivative is you make a Taylor expansion for your objective function j, evaluated at your perturbed domain omega index theta. It will start like j of omega, and then you have the derivative, which is a linear form with respect to this variable parametrization of your deformation theta plus a small remainder term that must be small with respect to the norm in the space of C1 function. Okay. And then the main interest of computing this derivation is that, of course, if you want to decrease because you minimize your objective function, you are going to choose a vector field theta so that the directional derivative is negative. And then if you take a small increment, small descent step tau, which is positive, if tau is sufficiently small, this will allow you to neglect the remainder term in the Taylor expansion, and then in the direction of theta for a small descent step tau, you are sure to decrease the objective function, and that's the beginning of a gradient algorithm. Okay, let me give you in this first lecture only two examples of shape derivative, very simple one. The first one is when you integrate a fixed smooth function f of x on the domain omega. So the domain omega appears only in the fact that it is the domain of integration of your objective function. Then a classical result tells you that the directional derivative of your function j in the direction of theta is simply the integral on the boundary of the domain omega of the same function f multiplied by the normal component of the vector field theta. So to understand this, you just do this small sketch. So you see the domain omega with a boundary in black, and then the variation omega theta as a boundary which is a dotted line in red. And you can see that if theta is small, then the difference between the two domains is small, and the difference is concentrated along the boundary of omega, and the thickness of this difference is exactly theta dot n. Okay, so if you make the difference between the two integrals of f on omega and omega theta, then it's something which is carried by the boundary of omega with thickness theta at n, and then of course you still have the integrand f. So that's a kind of intuitive proof of this formula here when you make a Taylor expansion of your objective function. Of course, you can make a rigorous proof of this, and then this rigorous proof is really just a simple consequence of the so-called Reynolds or transport theorem, which is well known for people who do fluid mechanics, which is that if you compute the time derivative of an integral of a function that depends on time on a domain that depends on time, then by the chain rule lemma, it's a combination of first the partial derivative of the function f that depends on time on the domain omega t, but then you also have a contribution because your domain is moving, and this contribution is exactly of the same type of the objective function of the derivative of the objective function that we have just considered. In particular, if you apply this result to the function f, which is 1, then your objective function is just the volume, and then you recover that the derivative of the volume is simply the integral on the boundary of the normal component of your vector field theta, and by integration by part, it's the integral on the domain omega of the divergence of this vector field. And in particular, if you have chosen a direction of derivation which is divergence free, it's well known that it does not change the volume, so the derivative is going to be 0. Okay, a second example, which is very practical, is when the objective function is the integral again of a smooth fixed function j, but now it's an integral only on the boundary of the domain omega, d omega. And then the shape derivative in the direction theta is again an integral on the boundary of omega of the normal derivative of your function g plus the mean curvature, kappa is the mean curvature of the domain, times the function g, again multiplied by the normal component of your vector field theta. In particular, if you apply this result to the function g, which is a constant equal to 1, then the objective function is the perimeter, okay, and then it's well known that the derivative of the perimeter is proportional to the mean curvature. Actually, I have again a small sketch here that shows you a domain omega with a dotted black line, and then omega theta is the domain with the red boundary. And then it's well known that if you want to minimize the perimeter, you should choose a descent direction, theta, which is proportional to minus the mean curvature times the normal. And this specific vector field has a tendency to smear the bumps of omega. So you see here, you smear the bump on the red parts here, but on the blue part, you will seal the hole. So that means that you will try to have the more possible flat or convex shape that will, in some sense, minimize the perimeter. Good. More generally, there is a theorem which is called the Hadamard structure theorem that tells you that for any objective function j of omega, when you compute the derivative in a direction theta, it's always written as an integral on the boundary of some integrand v, depending on omega, times the normal component of your vector field theta. Okay, so this, of course, this integrand v index omega, that depends on the specific choice of your objective function, and in particular, that will depend on the state u omega, which define your objective function, and of course on some adjoint state, but we will review this theory in the next webinar. Okay, this is an integral that may hold in the sense of distribution. So what does that mean? That means that it may also depend on tangential derivative of your vector field theta, on the normal component of your vector field theta. Okay, one key consequence of this Hadamard structure theorem is that this derivative in the direction theta depends only on the normal component of theta on the boundary. So in particular, if your vector field has a normal component that vanish, meaning that what you do is you simply convect the boundary on itself, so it's only kind of a rotation, then it does not change your objective function because you do not change the geometry of your domain. Okay, so a tangential vector field, it's simply kind of a convection, or you just slide the boundary on itself, so that does not change the domain. So of course, the shape derivative should vanish. Nevertheless, if you choose a different vector field theta, in particular, if you choose a vector field theta which is proportional to the normal with a scalar coefficient in front of it, which is minus v of omega, you ensure that the directional derivative is strictly negative. And so by this change of the geometry induced by theta, you will decrease your objective function. Good. Now let's discuss how we implement those principles. And so the idea is to do, of course, a gradient algorithm that we will initialize with some initial guess omega 0. And then for every iteration n, we will compute the solution of your state equation u index omega n, then possibly an adjoint p index omega n. And then from those two state u and adjoint p, we can compute the shape derivative. And from this shape derivative, we can induce a descent direction theta n, and then we are going to move the previous shape omega n to a new shape omega n plus 1 by simply moving all point x in the domain to a new position, which is x plus descent step to n times theta n of x, where theta n is this descent direction inferred from the shape derivative. And then you iterate like this until you converge to an optimized shape. Okay, so this algorithm so far is kind of theoretical, and in particular, we have to decide how we update, omega n to omega n plus 1. How do we apply this vector field to your shape? So what was classical was a Lagrangian approach, which is more or less the approach which is used in geometric shape optimization, very classical geometric shape optimization. So what does that mean? Each shape omega n has a triangular mesh Tn, okay? And this triangular mesh, of course, is used to compute by the finite element method the state and the adjoint, right? And then the update from omega n to omega n plus 1 is simply realized by pushing the nodes of the mesh Tn by this vector field with a descent step tau n and times theta n. So what does that mean? You take the position x here of every node, and in the direction of the arrow, which is the direction of your vector field theta n, you move the points. Of course, the difficulty is that if your vector field or your descent step is too big, when you move the points of your mesh, maybe the new resulting mesh is not valid in the sense that you have inverted triangles. Okay, you may have very flat triangles. So the difficulty when you do this is that you need to check that the new position of the nodes of your new mesh are still valid, and maybe you need to remesh because the elements of your mesh are not of a good quality, inverted, too flat, or whatever. So that's the classical difficulty when you do a geometric optimization, that when you move the nodes, maybe you need to adapt or to remesh at some point. Nevertheless, it works, and let me show you an example for a so-called cantilever problem. So you see the geometry, the dash part is where the structure is fixed, clamped. On gamma n, on the right part, you have this vertical load, and I start an initial configuration with 7 holes, and then I minimize the compliance with a constraint on the volume. So you should see the movie where you see the mesh, which is deformed, of course. Each iteration is computing a derivative on moving the mesh. So it seems to work pretty well, but you see it stop at some point, and actually it's not even a local minima. It's not even a local minima because the leftmost bar, vertical bar here, becomes thinner and thinner, and at some point it wants to become so thin that the meshing algorithm cannot mesh the new mesh, or you invert triangle. So actually it does not converge because it has reached a local minima. It stops at some point because the meshing algorithm tell you, well, I cannot mesh, I have too small elements in this thin bar. So the algorithm really wants to break the bar, okay? So that's the limit of classical geometric optimization, and the interest of the level set algorithm is that we are going to go beyond this limitation of geometric shape optimization. So a few words about the level set method. So as I told you before, this was devised by Osher and Sitian in '88 to represent, to help them to solve a combustion problem. And here is an example. Maybe I should, I think it will cycle, so you will see it again. This is an example in fluid mechanics. That's a collapse of a water column. Blue is water, red is air, and you see how water under the action of gravity is falling down, and you have this interface between water and air, which is described by a level set function. So that's a classical application of the level set algorithm. There is a picture below on image segmentation by the method of so-called active contour, which is again using level set. So these were previous application of the level set. But of course, today we are going to discuss application of the level set method for shape and topology optimization of mechanical structures. Good. So first, let me come back to the Lagrangian point of view when we have a family of shape, omega of t, which are evolving with time. So there is no time in optimization, but in some sense you could think about time being a pseudo time corresponding to the descent step. So we have a family of shapes which are better and better for optimization problem indexed by the descent steps or the pseudo time t. So those shapes evolve, have a boundary gamma t, and they evolve with some given velocity field v of t on x, and this v correspond to the previous vector field theta, which was a descent direction. Okay. Now let me define the concept of characteristic curves. So for a point, initial point x0, chi, depending on the initial position of x0 and t, is a solution of the ODE, where the right-hand side of the ODE is this velocity field v evaluated at the same point chi. So that's exactly what we call characteristic. So if you see On the picture below, I have a plot of my vector field V, that's the blue arrows, and starting from some point x0, I have a line, which is the solution chi of this ODE. So that means that at every point on this line, the tangent vector field is exactly my vector field V. Of course, for some different initial point, x0, x1, and x2, you have different characteristic curves. And so an intuitive definition of an evolving domain is that omega t is just precisely the set of points chi, which are on the characteristic curve that started at some point x0, which was in my initial domain omega 0. So that's a precise definition, a Lagrangian definition of an evolving domain omega t. So you have a sketch of this definition below. So if you start from some domain omega t0, you take a point x0, let's say on the boundary of this domain. So you evolve along your velocity field v, and you arrive at some point t on the characteristic point chi starting from x0 at point t. And that defines a new point on your domain omega t. Okay, so that's a definition of evolving domain based on solving ODEs, computing characteristic curves. So this Lagrangian viewpoint is very nice, but it has a big drawback, which is exactly exemplified on this picture. Imagine that the velocity field is such that the boundary of your domain, the velocity field here is in red, at some point they will cross. So now the boundary of your new domain has crossed, and then there is a very tough question, because this intersection zone here is both inside view from the right, but it is also from the outside. So you have to decide, am I inside or am I outside? So where is my domain? In particular, if you have to compute your velocity field by knowing where is the inside or the outside, or by knowing what is the normal vector of the curvature vector, at the intersection point, you have two normal vectors. So which one is the right one? Okay, so you have a difficulty, which is a classical difficulty for Lagrangian method. And then the main idea of the level set method is we are going to completely forget about this Lagrangian setting. In this Lagrangian setting, by the way, displacement is reversible, because you could solve the ODE for the characteristic curve for positive time or for negative time. So if you just revert the sign of the velocity, you can go back and forward. It's completely reversible. The level set method is going to forget about the Lagrangian setting, forget about reversibility, and it will use now a Eulerian setting, which will be irreversible, and that will give you a definition of what happened after crossing boundaries. So the idea, as probably most of you knows, is to introduce a function phi, which is called a level set function, which is going to be by definition zero on the boundary, negative inside, and positive outside. Okay. So for example, if you have a shape here of this cartoon character, you define a function here, which is represented in 3D. This picture here is in 2D. The function phi is now in a higher dimension. It's negative, so blue inside the yellow region of your domain omega, and it becomes increasingly green and red outside, so positive. Okay, so that's one way of representing a shape. Of course, there are many such functions. And usually we prefer to take the one which is a sign distant, but any other function will do the job. The first interest of this is that it defines implicitly the geometry, and in particular, it is the computation of a lot of geometrical quantities like the normal vector. So if you look at the normal vector, one definition, if you have a level set function, is that it's also equal to the gradient of your level set function divided by its modulus, at least where the gradient is not zero. And then that gives you also an extension of the normal vector, not only on the zero level set, but on any value of the level set function phi of x being equal to a constant. So you have an extension of the normal vector everywhere. Similarly, you can compute the mean curvature, which by definition is the divergence of the normal vector. So you can compute mean curvature everywhere again as an extension. And of course, you can use this level set function by means of an Heaviside function to compute integrals of another function defined on the domain omega or on its boundary gamma. Good. Now, what is the equation for the evolution of such a level set function? So let me come back to my Lagrangian definition of evolving domain. So starting from a domain omega 0, if it evolves according to some velocity field, I have a Lagrangian definition, but now I want to translate this Lagrangian definition into an Eulerian definition of a moving domain. So remember that, again, only the normal component of the vector field V matters if you have a tangential component, right? Like it's plotted here on the left picture. It's only a kind of sliding the domain on itself. So the green part will simply move on a new position. The red part will move to a new position, but you do not change the general form of your domain. So we can really ignore the tangential component of V that does not matter in the transformation of your domain. Okay, so when you have a domain evolving according to a velocity field V, there are three different cases. The first case is when the velocity field V does not depend at all on omega t. So V is defined on transport world. So that's what can be called a passive transport. That's the easy case. A second, more complicated case is when V depends on local features of omega. So what do I mean by local features? Typically, it depends on the normal vector n or on the mean curvature. So that's quantities that are computed locally at every point x on the boundary. And then the third cases, which is a case of interest for us, is when V depends globally on the domain omega because, for example, it depends on the solution of a model of a PDE posed on the domain omega. So that means that you need all information on the domain to compute the velocity. It's not just a given local formula. Okay, let me give you some example of the easy case, which was actually the original example of Osher and Sitian, which is the representation of omega t being a burnt region. So that's the region where the gas has already burned. And the combustion is represented by the fact that the velocity which evolves the domain omega, the burnt region, is proportional to the normal vector with a constant normal speed. So c is a constant, positive, and then you see the evolution of the region of the burnt gas. It's simply an evolution along the normal with a constant velocity. So you start with a small bubble and then the bubble increase from left to right. Something which is a little bit more complicated, because here in this case the velocity depends on the property of the domain, is the evolution by the mean curvature. So that's also a classical problem. So the velocity field is minus the mean curvature times the normal. And you see the evolution from the left to the right, and you see that this has the influence of this type of mean curvature flow is that it will fill the bump, fill the crease, and flatten the bumps. So that makes this non-convex initial shape become more and more convex like it is. And actually, it is a theorem proved by Grégoire that in the end, any shape, even if they are non-convex at the initialization, will end up in something which is convex. Okay, in a more general setting, let's look at what will be the evolution equation for the level set phi that represent an evolving domain omega. Okay, so if by definition phi is always zero on the boundary, okay, you can replace a point x in a boundary by the characteristic the solution of the characteristic equation chi starting from a point x0 which was initially on the boundary of the initial domain. Okay, so if x0 was initially on the boundary of the domain, chi of x0 at time t is on the boundary of your moving domain. Okay, so by definition of the level set function, this should be zero. So now I differentiate this definition the level set function being 0 on the boundary, I differentiate it with respect to time. Time appears at two positions in this equation. It appears first as the dependency on the level set function phi, but it also appears in the dependency of the characteristic curve. So that's why I have two, when I differentiate with respect to time, I have two terms. First, the partial derivative of phi with respect to t, and second, by the chain rule lemma, the gradient of phi multiplied by the time derivative of the characteristic point. And this time derivative, this is by the ODE equal to my velocity capital V. Right? So I get the first level set equation, which is just an equation of advection for phi, d phi over dt plus v, which is a vector field dot nabla phi equal to 0. So that's the level set advection equation. But remember, and that's very important, only the normal component of the vector field matter. Everything which is tangential does not change the shape. It changes maybe the parametrization of the shape, but it does not change the shape. So actually, only the normal component is important. So let me replace capital V by only its normal component, small v, and then the normal field in the level set setting can be represented by nabla phi divided by its modulus. So if I replace capital V by this representation where only the normal velocity matters, I end up with a new version of the level set equation, which is an Hamilton-Jacobi equation, which is a nonlinear equation because you see that you have the modulus of the gradient, so that the norm of the gradient, so that makes the equation nonlinear. But the interest of this equation is that it is guaranteed that you always evolve in the direction of the normal vector at every time. So that means that you are always very efficient. It's in some sense a more efficient way of writing the evolution than the previous one, because in the previous one, maybe you do some unnecessary advection in the tangential direction, and that is not good because that may, from a numerical point, add numerical diffusion. Good. I did this computation for the zero level set, but the same computation work if I was looking at the C level set. So if I was looking at phi equals C, the same computation holds true. So that means that my equation for the level set advection or the Hamilton-Jacobi, they hold true everywhere because everywhere you sit on a level set of phi equal to some constant. Okay? Good. Now, of course, the evolution depends on this definition of this velocity field, and that's something which is very clear if your domain omega and your velocity field are smooth. But what happens if singularity appears? And it turns out that even if you start from very smooth initial shapes and you have a very smooth vector field, at some point singularity will appear. Let me explain that in a very specific setting. That's my initial domain here in yellow, and I'm looking at this part of the boundary, which is a kind of curved part, and I'm looking at a very simple velocity field V, which is simply equal to the normal vector. Okay, so that means that I'm advecting with a constant velocity 1 in the direction of the normal. And I plot here different position of the boundary of the domain after some increasing time. So you move in the direction of the normal. So the normal is towards the exterior. So you see that you move, and at some point you arrive at this red curve where the blue point is a singularity. It's a corner. Let me explain why you end up in a corner. Because if you end up after the corner is here, this red curve, then you have exactly this process of crossing domain. Okay, so if you do a Lagrangian evolution of all those points with velocity 1, you end up after this first point of singularity with boundaries which are crossed, because if you move the points independently, well, you end up with a multifolded boundary. So what is the meaning of this? And the idea which was proposed by Osher and Sitian was to impose a kind of an entropy criterion saying what is burnt, so this yellow part is burnt, will stay burnt. So that means that all this triangular part is completely irrelevant. That's inside the domain. So you should eliminate this crossing. And so what should be retained by this entropy criterion is exactly only the part which is not intersected. So eliminate this triangular part here, and that's what is the correct boundary in the sense of the level set equation.
Sorry
Okay,
to
so
cut.
singularities are
Sorry to cut
inevitable.
in quickly. I just wanted to let you know we have about 8 minutes left.
Okay, good. So I should go a little bit quickly. So so there is a notion of viscosity solution that explains this in mathematical details, and I'm not going into more details, but that's exactly a big picture here showing the same idea. That's the way it evolves, and that's the way it allows you to change topology also. So, for example, you see on this cantilever example the evolution of the level set equation and the change of topologies that correspond exactly to this notion of viscosity solution. Good. So I pass the floor to Charles.
Yes, so maybe I can share my slides on my own. Okay, and can you see my screen?
Yes.
Okay. All right, so thanks for passing me the hands. All right, so let's now deal about how we are going to actually solve level set equations on the computer. So as Grégoire said, we have a shape, the setting is this. We have a shape omega t that describes an evolving shape, and it is described by a level set function, meaning that omega t at any instant t is the set of points where phi is negative. And it evolves through a velocity Vtx, a normal velocity, which in our case of shape optimization describes the shape gradients. So the Hamilton-Jacobi equation reads like this, exactly like what Grégoire presented. And the velocity field is actually very complicated. At any point t, the shape gradient is going to be some kind of taste of the shape derivative of the objective function under minimization. So the only thing that we can do possibly is to freeze, to cut the time interval into a series of subintervals, and on each such subinterval to freeze the velocity fields, meaning for all time t in the period tn plus 1, Vtx will be frozen to its actual value at Tn. And then we are back to solving a steady state Hamilton-Jacobi equation with a normal velocity v of x, like this. So how are we going to solve this equation, which is not at all trivial because it's a nonlinear equation. It makes appear here the absolute value, the norm of the gradient of the function, of the solution function phi. So we are looking for first order Hamilton-Jacobi equations, and there is a well-established theory to solve such equations, which appeals to the theory of viscosity solution that Grégoire mentioned. So it proposes in particular adequate numerical schemes to catch the good solution, the good viscosity solution to this equation, the one that has physical sense in the sense that it imposes this kind of entropy criterion in the cases where it is relevant. And the key point in the device of such schemes is the word upwinding. So that's what I'm going to explain in a simple case where we are in 2D and the computational support is a Cartesian grid. So just to try to give a hint of why upwinding is needed, let's consider the very particular, very simple case where the normal component of the velocity is constant. It's c, it's a positive constant. Then it's after some math, rolling up the math, you can see that the viscosity solution to this guy is this function here. It's a distance shifted by the coefficient c of t, meaning that when c is positive, then the level set function, the zero isoline of the level set function, we do that with rounding corners that go away and away from the square. And when the velocity, normal velocity is negative, then the shape will shrink into itself like this. And the corners here, they will stay corners actually. So what you see is that there is some kind of irreversible pattern that is happening here, because if you shrink and then go back in the other sense, then you will see that the corners that appear here will get rounded, meaning you don't obtain the same thing by applying the forward solution of this Hamilton-Jacobi equation, then backward or the other way around. There is some kind of irreversibility here that only upwinding can catch, and there has to be some kind of translation of that in the numerical scheme. So there is something that will appeal to people, that speak to people that know a little bit about hyperbolic equations, if you consider the equation that I mentioned in 1D, and formally that you take the derivative with respect to the spatial variable in this guy, you obtain this one-dimensional hyperbolic equation. Then it's well known, in some sense, in this world, that the theory of shock waves predict that if you consider very simple data here with a value UL on the left part and the value UR on the X on the right part, then depending on the values of UL and UR, you may have a shock wave or a reflection cone. The shock wave would correspond to a sharp corner for psi, and the reflection cone will correspond to a rounded corner for psi. So this is really something that tells you that you need to do upwind schemes to find this very particular behavior of the solution. So how do you do in practice? So let's consider the very concrete situation where we have a Cartesian grid of space. We discretize the time by a series of time steps like this, and we discretize the space by this Cartesian grid, which is here with a step size delta x and delta y in the x and y directions. So we introduce the finite difference quantities di plus jx and di plus j minus, which is here. And this quantity here is just taking the value here minus the value here and to divide by delta x. And when I consider the minus x, then I'm basically doing it backwards like this, Vij minus Vi minus 1j, etc., etc. So the level set Hamilton-Jacobi equation can be solved by this particular scheme here. So this is an explicit first-order scheme where the update is this discretization, this seemingly weird discretization here of the gradient term, which is over here, sorry. And this is exactly what we need because it features discretization, nabla ij plus and nabla ij minus of phi, which are upwind and downwind discretizations of the gradient norm, which is here. Why are there upwind discretizations? Because they only use values among the neighbor values of Vij that are larger or smaller depending on whether it is downwind or upwind, respectively. So meaning that the discretization of the Hamiltonian, which is here, if you just look at this formula in the eye, then you can see that it is upwind in the sense that if Vij is positive, then this value is used for the discretization of the gradient norm, which only uses value of Vij at a point ij that are less than Vij, that are smaller than Vij. And if Vij is negative, meaning the information goes in the other sense, it only uses values of among the neighbors of ij that are larger than Vij. And this scheme can be proved to be convergent to the unique viscosity solution to the Hamilton-Jacobi solutions. So this seems a little bit weird and a little bit difficult, but really the formula is like this. And if you program this like this is like 10 lines in Python, and it works exactly it does exactly what you need to solve the Hamilton-Jacobi equation. So you also have high order variance of this strategy, and all these things, you have very nice numerical packages that allow to solve this equation. So another point that is very important in the numerical practice of the level set methods is the need to initialize or redistantiate level set functions. So as Grégoire mentioned, there is not one level set function associated to a particular shape. There are a lot of them, but there is certainly one which is more beautiful than all the other ones. This is the sign distance function to the shape, which is minus the distance to the boundary when you are inside, 0 when you're on the boundary, and plus the distance to the boundary when you're outside. So this is a 1D visualization of an arbitrary level set function of the interval 0, 1, and this is a visualization of the sign distance function to this interval. And this solution is often preferred because it has a unique gradient norm, almost everywhere. Here, it's very important in numerical practice to have level set functions that are close to sign distance functions. This is not something that the theory dictates. This is something which is dictated by the need for accuracy. It creates numerical artifacts when you don't have this feature. So in practice, it's important to initialize distance functions as sign distance functions, and it's important also to periodically reinitialize the current level set function as a sign distance function. So you have adequate schemes based on the force matching method, for instance, to do that. And I'm not entering into any more details for lack of time, but these are classical issues in the numerical practice of the sign distance of the level set method. So here are some final clues about the level set method. It's usually very cheap. It's easy to implement, at least on Cartesian grids. You have very nice open source libraries on the web if you don't want to implement them. They are very, very cheap. They are some kind of linear or n-log-n like algorithms. And in the next webinar, we'll see how to implement this type of techniques on computational support that are not Cartesian grids, but are triangular grids, for instance. And so, Grégoire, I think the floor is yours.
So here is an example for compliance minimization under volume constraint. So it's a so-called electric pylon where you see some loads which are applied to the blue points. Oops. Yeah, and here is the movie. So the initialization was a full domain, and in 3D, because I'm sure I will have questions, in 3D, change of topology are very easy because most of the topologies that we are looking at are handles and not internal holes. While, of course, in 2D, change of topology is a bit more complicated. There are some obstruction, and so that's why we very often initialize with a so-called Swiss cheese initialization with many holes. But again, is another example of a so-called dome, which is optimized under hydrostatic pressure with 5 anchor points, which are red at the bottom. And again, this one, you see that the initialization is completely trivial, but it's able to change topology very easily. So change of topology is much easier in 3D than in 2D, where I must admit it's a bit more tricky. All right, here is an example of a compliant mechanism. So we act on the blue part and we want the jaws, which are red, to close. And you find this optimal gripping mechanism, which is in the undeformed configuration on the left, and deformed. You see that the jaws indeed are closed on the right. Again, a very complicated topology has been obtained with the level set method. It works also for other objective functions. So here is an example with LP norm of the stress, which is concentrated in this corner here. So the optimal shape for compliance is this one. And if you do an LP norm for p equal to 2, 5, and 10, you see that for 10, indeed, you get a rounding of the corner as should be expected, which makes a big difference with a compliance solution. Okay, to conclude, there are some assets of the method and some drawbacks. Clearly, one drawback is that the shape is not mesh exactly. That's the same drawback as for density method. And in particular, the choice of the ersatz material could be tricky for the design of compliant method. It's quite sensitive to the initial design, but mostly in 2D. And then admittedly, it may be a bit complicated, but actually there are many open source libraries, as Charles said, and so that should make the implementation of the level set method easy for newcomers. Thank you for your attention.
Yeah, thank you for your attention.
Thank you so much. So we have some questions, so I will just ask them for the people who have submitted them. So one question is, why does the shape derivative only depend on the normal component of the vector field on the boundary? In practical simulations, how do you compute the normal vector accurately on complex meshes?
Okay, so why it depends only on the normal component is exactly explained by this kind of a picture, because if you move tangentially, it's only a kind of sliding of the boundary on itself, so you don't see any change globally. Okay, so if you have a vector field that moves tangentially, you don't change anything, so the shape stays the same. So that's why it has a zero derivative. So only the normal component matters. Now, how do you compute the normal vector? So the starting point is to say that this was maybe before, sorry. Yes, that's here. If you have a level set function, nabla phi divided by its modulus is an extension of the normal vector. So that's one way, kind of naive way of computing the normal vector. We'll discuss maybe some details in the next webinar for more general meshes.
You have actually a lot of methods to do that. You could do that by exactly this formula that you use Grégoire. You could use this formula with a least square taste. You could use some kind of larger stencil reconstruction. Some people also, when you work on Cartesian grids, use essentially non-oscillatory finite differences. So, I mean, you have like a lot of numerical methods to do that. But when you are in a level set context, it's probably better to use to do something based on the formula that Grégoire pointed out.
Okay, thank you. So we have a question that came quite early on, so potentially it's been answered on the way. But so what is the simplest way to connect the shape derivative of the objective function? Oh wait, sorry. What is the simplest way to connect the derivative of the objective function to the shape derivative? Is it as simple as using the Hamilton-Jacobi equation to connect the normal velocity to the time derivative of the level set function?
We'll discuss this in details in the next webinar. So that's what we call the Hilbertian extension.
Okay,
So yeah,
great.
sorry not to say more, but that will be
Yeah.
typically the topic of the next webinar, one of the topic of the next webinar.
Great. So then, Farzad, you will need to come back next time.
Yes, I'm sorry about that.
And we have another question. So in the iconal equation, can C be 0? What would happen to the shape then?
Well,
Will not change.
nothing happens. If the
That's
velocity is
zero
zero,
velocity.
the shape stays the same.
Yeah.
Okay, yeah. And do we need reinitialization even if we do small displacements and then extract our contour of interest?
Actually, redistanciation, it's really something like a bit empirical. I mean, you need to redistantiate not necessarily at every step of the practice of the method. You need to redistantiate often enough to have a level set function which is neither too steep nor too flat, and possibly not too often to avoid that it be too large computational burden, or to avoid perturbing too much the level set function. So it's a bit, usually you do redistantiation every 4 or 5 iterations, but it's really something like depending on the sense of the wind.
Yeah. Then there's one question I'm not quite sure I understand what they mean, but it's is the level set solved on immersed Cartesian grids?
For the moment, in this presentation here, we have presented very briefly a discussion of the algorithm for the Hamilton-Jacobi equation here, which was on Cartesian grid. So admittedly, for the moment, we discuss only the case of Cartesian grid. So that means that, for simplicity, you could take the same mesh for your finite elements, but we will discuss the same solution of algorithm, but on simplicial mesh next week, next webinar, sorry. So
Okay.
for the moment, we discuss only the case of Cartesian grid, but we will discuss the case of simplicial meshes next webinar, sorry.
Well, it is actually next week.
That's next week. Okay, okay.
Yes,
I don't remember.
That's okay. And then yeah, that's the questions we have for now. If you have any more questions, come next time and ask them. And also, I know you have posted the slides on Charles's website.
Yes.
So maybe you have the link here, or otherwise it's
just a minute. Yes, yes, okay,
I have
because
it here.
it was before people got connected.
Yeah,
So I will put the link in the
yeah.
chat. Yes, does everyone?
That was only for us. I put it for everyone here. So
Okay.
here's the link if
Okay,
everyone wants to see. Yeah, thanks a lot. So I will just steal the share again,
Please.
and then I will just show that the next 2 lectures in the series are next week. So that's next Wednesday, the 20th, and then the week after on the Thursday. And you can go to our website. There you can find the Zoom registration links. So just Google top webinar, and you should find it.